Okay, I'm going to talk to you about some of the challenges we're experiencing at NASA regarding the search for life outside of our own solar system. So scientists are getting pretty close to 6,000 confirmed exoplanets. If you do the extrapolation and factor in the sensitivity of various instruments, it's clear that there are over 1 trillion planets in our galaxy alone. So the question is no longer, are there planets in our galaxy, but are there life forms anywhere? So the way we do that is we do it with the Space Telescope, because we can't go there. They're just too far away. So this Space Telescope ideally would capture the reflected light from the star bouncing off the surface of the planet, or maybe off the clouds or off the ocean. And then, as we've done for over 100 years, we do spectroscopy. We look for evidence of oxygen, ozone, carbon dioxide, water vapor, and then try to piece together the story. Now, there's one problem with that, because the spectroscopy part is the easy part. The hard part is the fact that it's not just the planet light that we are receiving, but it's lots and lots and lots of photons from the star. So this is what I call the contrast problem, where the light from the star is about 10 billion times brighter than the reflected light from the planet. So I use an example for the public. It's like trying to find a firefly that's fluttering around an extremely bright object, like a lighthouse. And you put the lighthouse in my home state of New Jersey, and here we are in the Bay Area. So just fathom trying to put all that together and trying to achieve the spectroscopy part. So these are some enormous challenges. So what we're trying to do is take a star like this, add some type of occultation or a mask, if you will, block out the light from the star, and there you see in this picture the actual image of a planet. And now we can do the spectroscopy. So the hard part is the starlight suppression. And there are only two ways that we're looking at NASA. One is using a mask or an occulter, internal to what? Internal to the telescope, and we call that a coronagraph. If you want to take the mask and put it outside of the telescope, that is then called an external occulter or a star shade. So let me tell you really quickly about the internal coronagraph, because that's a little bit more mature, and we have plans to actually fly that. So we do it with the Space Telescope. The light comes from the star. As it bounces around the optics of the telescope, it starts to get slightly deformed, because nothing's ever perfect. And then you see it on the camera. We put in a mask to block the inner core of the starlight. That mask will redirect the light to the outer edges of the beam. We put in another optical component, like a washer, and that blocks out what you would think is most of the light. The problem is those deformations that we talked about. I'll get back to that. The planet light, if you remember, comes in at an angle. So the planet light will miss altogether the masks, and it will end up on your science camera. The problem is the deformations. The deformations in the optics, even if you think they're perfect, are still too large, and they scatter the light. So what you see now is that the deformable mirror is actually moving in space, and the deformable mirror is correcting or compensating for the imperfections in what you think are perfect optics. And that's how we then find, you see that little blob of light on the left-hand side, that is your planet. Now you can do the spectroscopy and all is good. So that's a very challenging set of optics that I just showed you. I manage a lab at JPL that has probably the most sophisticated set of coronagraphs in the world, and we are advancing them to meet the next level of requirements, which is basically looking for Earths. So this is what it looks like on the inside. The challenges that we're experiencing are the optics. The optics have to be designed and manufactured exquisitely well. You can't have any contamination. Those deformations I told you about that naturally happen, we have to sense them. We have to sense how bad are they, and then we have to correct them. And then when the telescope is in space, the level of stability is really unheard of. It's basically tens of picometers of stability is required, both thermally and dynamically. So this is a great challenge. I will say in the lab, we are probably about an order of magnitude away. So about a factor of 10. So we're getting close. We're not there yet, but this is where the investment is required. The good news is NASA is going to fly one of these things in the next 12 to 18 months. This coronagraph will be the first actively operated coronagraph in history, and it will be able to detect Jupiter-like objects. So it's a step in the right direction. It will not be able to do Earths. Earths are going to require a lot more time. And so this is a mission that NASA has just started. It's called the Habitable Worlds Observatory, and it will definitely be designed to look for Earths. So stick around. That'll be hopefully launched in the late 2030s, depending on funding, or maybe slip into the 2040s. So it's a long time. Exciting for this conversation is that this telescope is also being built to be robotically serviced in space, and that's an exciting area that I take a lot of interest in. All right, with the time I have left, let's flip over to the starshade. So this is not science fiction. This is our concept. The object on the right is a telescope. It's a run-of-the-mill telescope, if you will. The object on the left is the starshade itself. You see the petals have now unfurled. The inner disk has deployed. So you have two spacecrafts that have to fly in formation. Here you see the telescope is patiently waiting for the starshade to fly in the direction of a star of interest. They align themselves, starshade, and telescope, and there you wait until the alignment is achieved, and now there you go. You see the reflected light from the planet. Now you can do your spectroscopy. So this is the second way of doing what we call starlight suppression. What you just saw is the starshade itself is the size of a baseball diamond. Its job is to put the telescope in a shadow. And so if you look at the star, its light is reflected off the planet. That blue line, the planet light skirts the edges of the starshade, makes its way into the telescope, and there you can do your spectroscopy. The challenges here are multifold. It's hard to deploy things the size of a baseball field in space. Micrometeoroids is always a problem. James Webb is experiencing that now. It's not the micrometeoroid impacts to the inner part of the starshade, it's the edges that we worry about. And then lastly, NASA hates when you can't test something exquisitely. So we can't test a full-scale starshade in space because you can see that the separation between the two spacecrafts can near up to 100,000 kilometers. So we end up having to do a lot of subscale testing, and we rely on modeling to be able to tell the story. So here's a lab that we funded for a Princeton scientist. It's in the basement of their chemistry building, and basically we simulated the star with the laser. You see the camera on the left, that's the telescope, and then in the middle is our subscale starshade. But I'm happy to announce that this setup actually met all the requirements right off the bat. So we're very excited about this approach. At JPL several years ago, we wanted to just see if we can build something simple for deployment. And with 4 Mach petals, we were able to build this fairly quickly, and it actually met all its tolerance requirements. The tolerance requirements are in millimeters, so it's a lot easier in some respects. You see the starshade here is transparent. Transparent doesn't work. It's got to be opaque to block the starlight. So we needed some origami scientists and mathematicians, and they came up with a wonderful design. This actually made the cover of National Geographic. And so the origami of, this is 3 layers of Kapton, deploy just naturally. In fact, it just wants to deploy. And we convinced ourselves that this is, well, we're on the right track. And so this is where we're leaving it. This project is going to basically come to a funding conclusion because the coronagraph is just so much more mature, and we want to leverage previous investments. But there are other applications for the starshade in the future as well. So I'll stop there.
Hi. So you're simulating with a laser stars far away with exoplanets are basically point sources. And so you're eclipsing the point source with this ginormous thing far away, so to the telescope it looks really small, right?
Right, so, and it can't be so large that you block out the planets.
Right. Since it's so large, it's very far away. The alignment problem you kind of glossed over of aligning 2 spacecraft in a line with an infinitely far away distant object when they're kilometers apart. Is that a solved problem, right? The alignment between the spacecraft?
Right, that's a great question. I didn't put it as a challenge. We actually solved that problem. We did it 2 different ways in the lab. We haven't done it in space yet. The reason we're so confident in that particular case is because your sensor is the size of your telescope. So if your telescope, in this case, is a 6-meter class observatory, 6 meters is massive. And so being able to to detect the starshade and stay in alignment is actually very straightforward.
We had a question over here, I think. Was it you, Adam?
Where are you parking the coronagraph?
So great. So the coronagraph is internal. It's internal into an instrument. It's in the back end of.
Sorry, the spacecraft. Where are you putting the spacecraft?
Oh, the spacecraft. Sorry. I guess the cool place to go these days is Sun-Earth Lagrangian 2. It's a stable point in orbit. James Webb is there. It's showing a lot of success. So that's where it would go. You want to put it in a very low stress, low dynamics, low thermal environment.
Right. We have time for one more.
It could be many different things. Right now, we are just baselining a hydrazine concoction, which is what we've used in the past. It's a big surface area, so it can be used for solar power, right? Which we're also experimenting with. So there are a lot of possibilities, and there's discussion about how to service the Starshade because it's going to run out of fuel, and so that's also another opportunity.
Wait, one more. Oh, sorry.
No, sorry.
Okay, over here and then over here. Then we
Sure.
Great presentation, Nick. Thank you. So one of the interesting things we've learned about exoplanetary systems is they don't look very similar to the solar system.
Yes.
So what can we learn about the solar system that can inform our study of exoplanets and vice versa?
What can we learn about exoplanet systems?
From looking at the solar system, and what can we learn about the solar system from the exoplanet research that you're doing?
Wow, that's a great question. I mean, what we've learned just from the results from Kepler is the diversity of the systems. We thought our system was typical, and we're finding out that it's absolutely not typical. So where the Jupiters are is really important because they cause mass chaos as they migrate, and so that has an impact on rocky planets. We're biased towards rocky planets because we think that's the best place for life to form, but we don't actually know where to look for the rocky planets. There have been very few rocky Earths discovered through indirect means like a transit. There's probably a lot more to say, Heather. I'll just stop there.
Thank you so much. That was fantastic.